Today we're going to talk about the third method of solving systems called the elimination method. So this elimination method is probably the one that most of us will use more often than the others. Although graphing method works great for certain situations, the substitution method works great for certain situations, but I do think the elimination method, once you really understand it, is probably the most preferred method as you go. So there are still some steps that we need to kind of work through and understand. So step number one, what we're going to do with this system is we're going to make columns of like terms. So remember, like terms, A's with A's, B's with B's, X's with X's, Y's with Y's. So we know a system is more than one equation. So what we're going to do is take our two equations and line them up so that we make columns of like terms. And what I wrote here in the parentheses, which will make more sense as we go through them. X's will be over X's, Y's will be over Y's, the equal sign will be over the equal sign. If there were any numbers, they would be over plain numbers, all the way through so that all the columns line up. So step two, and we're going to change these numbers over here a little bit. This is really step two. We're then going to multiply one, sometimes both, but one equation by a constant, which we know means just a number, so that one pair of like variables has the opposite coefficients. So let's just talk quickly about that. So remember, a coefficient is a number in front of a variable. So if I had the coefficient, if I had 5a, for example, the 5 is called a coefficient. Remember, the word opposite would mean one's positive and one is negative. So for that same 5a, the opposite coefficient would be negative 5a. So opposite coefficients, the coefficient being in front of the variable, the opposite meaning the same number, but the positive versus the negative. So then we go on to the next step. So for step three, now what we do is we add the two equations together. And because one is opposite of the other for the coefficients, we'll eliminate one of the variables. So maybe the x's are eliminated, or maybe the y's are eliminated. For step four, we're then going to finish solving the equation from the addition for the remaining variables. So let's say that x disappeared. We would continue to solve so that y was all by itself. Step five is we're going to substitute the value that we just got from step four into one of the equations and solve for the other one. So if we solve for y, we get that answer and we plug it back into one of the original equations to solve for the x. And lastly, step six, remember to check our solution in both equations to make sure that that solution works in both. Can't just work in one, it does have to work in both. So that's an awful lot of words, that's an awful lot of just kind of blind steps. Let's see how a few of these are going to work together. So here we have a system. X plus 3y equals negative 2. X minus 3y equals 16. We want to solve by elimination. So let's just kind of go down through the steps. So the first step says make columns of like terms. So if you look at this, this is what that means. So x's are over the x's, y's are over the y's, the equal signs over the equal sign, and the numbers on the other side are over the numbers on the other side. So step one here is done. I don't have to do anything for this one. Move on to step two. Step two says multiply one or both of the equations by a constant so that we have opposite coefficients on either of the variables. So let's look at that. So what is the coefficient in front of the x's? Well, I have a 1, which we don't see, and a 1, which we don't see. 1 and 1 are not opposite. Looking at the second one, I have a 3 and a negative 3. So that is important to notice, because these two numbers right here mean I have opposite coefficients. Because of this, I don't need to do that multiply 1 to make them opposites. They're already opposites. So because this is already now step 3, I can then just say add these two together. So again, because they're already in nice columns, and I already have opposite coefficients on one of the variables, I can just add. So now when I add, x plus x gives me 2x. 3y plus a negative 3y becomes 0. It doesn't become y, it becomes 0. So that is why we did this. So we eliminated the y's. On the other side, negative 2 plus 16 is 14. So then we look at step 4, solve the resulting equation. So this is the resulting equation. I just solve for x now. So we know to divide by 2, and I get x equals 7. We also know that this is not just my answer. A system needs to have the x and the y. So we found the x. So I'm going to start my answer over here. So I think I have the 7. But now I move on to step 5. So step 5 says to take this answer and substitute it back into one of my equations to find the y value. So not for really any reason, I'm just going to pick the first one. Sometimes there's a clear reason why I would pick one. So let's just go to this equation. We now have the x. So I can substitute the x out for a 7. And then, because now I'm only solving for one variable, I can get an answer here. And this goes back to the beginning of this year where we had multi-step equations. I would subtract 7 from both sides. I get 3y equals negative 9. Divide by 3. Y equals negative 3. So the x was a 7. I used that to plug into one of the variables to now come out with negative 3. Now, I'm not going to write the check here, but to verify this check, what I would do next is say, okay, so let's look at the other equation. So if this was now a 7 and this was a negative 3, I would have 7, negative 3 times a negative 3 is plus 9. 7 plus 9 is 16, so it checks in that one. And once I verify that it checks, then I can say this is the solution to this system. So that was an easy one because there were several different things that were already set up for us. Let's look at the next one. So on this next one, let's look through our steps. Are we lined up nicely? We're lined up pretty nicely. I don't really need to do anything to worry about this one. But then I look at the second piece. Do I have opposite coefficients? I don't see any opposite coefficients. I have a 5 and a negative 4. They're opposite signs, but not the same number. And these are both negatives and not the same numbers. So here is where I need to think. There's two ways I can go on this. I could make the y's opposite coefficients, and I'd have to multiply both equations by something. Or I can make the x's opposite coefficients, and I'm going to focus on the x's. So think about this. What if I said I wanted to change negative 2 into a positive 6? Positive 6 would then be the opposite coefficient of the top one, which is a negative 6. What would I have to multiply negative 2 by to make it a positive 6? Well, the answer is I would multiply it by a negative 3. Now notice that bracket that I put around the whole equation. Everything in that equation has to also be multiplied by the negative 3. So what I want you to notice here is this. When I go and do the multiplication here, let's just bring down this first one. Negative 6x. This one we're leaving by itself. And the second one is the one that we're going to change. So I'm going to take and use my distributive property, basically, and I'm going to say negative 3 times negative 2x is now a plus 6x. Negative 3 times the negative 4y is a plus 12y. And this is not really distributive property, but we're going to kind of just say everything has to get multiplied. So negative 3 times 14 is now a negative 42. I had to think in my head pretty quick there. So basically what we've just done, this equation right here is the same as this equation. As long as I'm multiplying any number by everything in the equation on both the left side and the right side, it still is the same equation, but we need it to look like this for this reason right here. I needed to have the opposite coefficients, a negative 6 with a positive 6. So now I can move on to that next step. Now remember, that next step is add these two equations together. By adding them together, 6x plus a negative 6x disappears. I get 17y. And on this other side, I get negative 17. The next step says continue to solve. So I would solve for y by dividing by 17. And this time I have the y value. So you've got to be careful here. The first one we got an x value. This time I have a y value. So now I got to be careful. So the y value doesn't just go in that first slot. It goes in the y for the x comma y. Then I'm going to take that over here and I'm going to plug it into one of the equations. Now, and again, no real reason for this one. I'm going to just go to this first one. So negative 6x plus 5 times negative 1. Notice I replace the y, not the x. Then I can continue to solve. Negative 6x minus 5 equals 25. I would add 5 to move it across the equation. Negative 6x equals 30. Divide by negative 6. X equals negative 5. So that would mean that we would now be plugging in negative 5 for the x value. And again, I do want to show a check, at least in my head here. If I plug in the negative 5 for the x to this other equation, negative 2 times negative 5 is 10. If I plug in the y as a negative 1, negative 4 times negative 1 is 4. 10 and 4 is 14, so that would help me verify that yes, negative 5, negative 1 is the solution to that system. So this next one is asking me to look at some different things. We have an A, B, C, and D, and decide which are efficient approaches to solving for that system. Doesn't mean there's one. Let's just see how many we have. So if I look through these, the first one, A, says add the equations. So what would happen if I added these two equations? Well, I think that would be a pretty efficient way, because notice these two negative coefficients right here, if I added these two together, I would eliminate one. And then, obviously, I still have a little more work to do, but I'm going to say, yes, that is definitely one of my answers. So I'm going to say A is definitely 1. That's going to be pretty efficient. The second one says multiply equation 1 by 2. All right, so if I take this first one and I multiplied it by 2, I would have 2x minus 4y and a 12. So that would look to be efficient, because I'd have this opposite. I'd have a negative 4 and a plus 4. However, notice what it says next. Subtract the equations. If I had a minus 4 and I subtracted 4, negative 4y minus 4y is now negative 8y. That's not really efficient. If it said to add these two equations at that point, then yes, I would agree with that. Looking at C, solve equation 1 for x and substitute the result into equation 2. That's very much the substitution method, right? So the substitution method says take one of these equations and solve for x. So they're saying take this first one, solving for x would mean add 2y to both sides to get 2y plus 6, and then substitute it in to the x over here to continue solving. That is definitely an efficient way to do it, because that is the substitution method. So I'm going to say for sure that's definitely a way to do this. The last one says to substitute negative x plus 4y for 6. Well, I can't replace 6 with something. 6 is a constant, so I definitely can't replace that one. So I'm going to say in this opportunity, A and C are efficient ways. Personally, I would say if you were asking me the most efficient way is letter A. The elimination method is a more efficient way for me to look at this, so I would say that A would be the best choice, but this is actually just asking for what is an efficient way. So A and C would answer that question. So next we want to look at some real life situations and these word problems, which are very much of a challenge. So in the first sentence, we are buying 8 hostas and 15 daylilies for a cost of $193. Your friend is also buying hostas and daylilies. They buy 3 hostas and 12 daylilies for $117. Find the cost of each daylily. So here's like a little bit of a guide to help us. But let's just first talk about what are we going to use for our variables. So the x, that's going to be the cost per hosta. The y is going to be the cost per daylily. Now again, there's too much information for one equation, which is why we're going to need to use a system to find out the 2 equations. So let's just do u first. So we had 8 hostas at some cost plus 15 daylilies at some cost, and our total bill was $193. Our friend only bought 3 hostas and only bought 12 lilies, and their bill is $117. Now, if we're assuming that we are at the same store, which we're going to for this situation, the price of all of those should be the same. So even though we have a different total cost and a different amount of hostas and a different amount of daylilies, we should be able to use a system to come up with our answer. So we do have these in nice columns. So because they're in nice columns, we can go right to step 2. We need to have opposite coefficients. So looking at opposite coefficients, I'm going to try to turn my coefficients into 24s. Definitely could have looked at 60s, maybe if you wanted to worry about the y's and try to figure out how to make that one work. I'm going to turn my x coefficients into 24 and a negative 24. So because of this, I'm going to have to multiply both of my equations by something. So here's what we're going to do. I'm going to multiply the top equation by 3. Then I'm going to multiply this bottom equation by a negative 8. And by changing these equations into something that I can work with, then we should be able to come up with our answer. So if I was to multiply the top one, here's my new equation, 24x plus 45 y's equals 579. And that's just multiplying the 8x by the 3, the 15y by the 3, and the 193 by the 3. Then when I do the bottom equation, now this turns into negative 24x. And that's really what we're aiming for, to have that opposite of 24's. Then minus 96y and minus 936. So I've changed my two equations. They are still the same equations, but they look differently so that this fits what we're trying to do. I have columns lined up. I have opposite coefficients on one of the variables. So that tells me I can go ahead and add them together. The 24x and the negative 24x eliminate. And again, that's really what we are trying to get here. So then when I add, I get negative 51y's. And on the opposite side, I get negative 357. I would finish this equation here by dividing by negative 51, and that gives me y equals 7. So now I have 7. So basically, the question is saying to me, what is the cost of a daylily? Well, think about that. The daylily cost is the y's, right? Right here. So do I already have the y? I actually do. They're not saying what's the cost of the hosta. They're saying what is the cost of the daylily? Well, I have that answer. So in reality, I don't need to continue here. The cost of the daylily is $7, and nowhere does it say that I need to know the cost of the hostas, so I've answered the question, and there it is right there. Now, if they had asked for the cost of the hostas, well, a little more work, obviously. I would take this y equals 7 and plug it back into one of these equations to solve for the x, and then I would find out what the cost of the hostas are. For those that would like to know, that's $11 if you've actually solved it for the hostas separately. So that's how you would do that problem. So just as a quick recap, if I'm looking at the different methods that we've talked about throughout this chapter, the graphing. The graphing was the first one we looked at, where you look for that intersection point. Not really the best method unless you have the graphing calculator, which will do all the calculating of the not so nice numbers. If you're just trying to estimate an answer, or when it lands exactly on one that you very easily can see on a graph, it's a good visual because you can see the intersection point. The substitution method is another one that we've looked at. This is a good one to use when you have one of the variables solved, like x equals 2y minus 3, or y equals 2x plus 3 on one of them, if that coefficient is a 1 or even a negative 1. But when one of the equations has y already solved for, or if there's a 1 in front of the variables. The elimination, if you have at least a pair that already has opposite coefficients, that's definitely a good one to use. Or if you can see that adding and subtracting won't eliminate them, but if you multiply one of the equations or both the equations like we just did with the lilies and hostas, you can get those opposite coefficients to eliminate. The elimination one is another good one to use again. Please make sure that you understand how this is working. This will end up being the one that I think most of you will prefer as you go forward. We do really want to understand how it works. And once you kind of get through how it works, it is actually pretty simple to understand once you learn those steps. Please make sure you are working hard on this, and if you have any kind of questions, reach out so that I can try to do the best I can to help.